impulse is, at its most basic level, equal to force times time. So that's what I've written here on the whiteboard. In that sense, you could say impulse is maybe analogous to work. Work was equal to force times displacement. And if you kind of look at things in a very, I don't know, maybe a very mathematical way, or if you kind of say like, well, hey, displacement represents a change in space, what about time, right? And in that sense, when you look at this formula over here in the key concepts, the first formula, it says I vector, so I stands for impulse. And this one says force average, so it says it's equal to force average times delta t. So maybe what I should, if I'd written this in a sentence, I maybe could have said impulse is equal to average force times change in time, and that's getting a little bit more into the details there. It's maybe a little bit similar to how work, like the naive definition was force times displacement, but there were more details as we delved into it. Directionally mattered a lot there. Part of the issue with force times displacement being work was that both force and displacement had direction, but work doesn't have direction. This is different in the sense that impulse is actually a vector quantity and basically inherits its direction from the force quantity. Time, though, does not have direction. I always find it interesting to say that because you could say, well, wait a minute, in those time travel movies, there's kind of like a forward direction if you travel backward. No, but no, time, as far as we know here, when we measure it, is not a vector quantity with a direction, despite what time travel movies might say about that. So in that sense, impulse really only has one place to get its direction, which is force. But since it says average force here, if I'm talking about a really complicated motion where the force is maybe continuously changing its value, including its direction, that averaging might get complicated. And it turns out there is a more complicated looking calculus-based definition, or you could say formula, that really amounts to like, well, how complicated does it get to calculate an average force? And the answer is, well, in the most complicated situations, you would have to use a calculus-based formula for average to get that. And we're totally not going to do that in this class. But we're going to be, for the most part, I think, intuitive. Definitely, though, so like kind of analogous to work again, we had like a simple formula that if the force was constant and the displacement was along a straight line, we could just say it was like, I think it was FD cosine theta if they happen to point in different directions. Again, that's not an issue here. So one could argue that this simple notion of force times time applies if force is constant. That's all you got to say because you can't say time is constant, right? Anyway, that's the kind of stuff we're going to usually use to look at impulse. Impulse is really, in my humble opinion, not as big a deal as work because work is really the whole like foundation for energy. So work is super important. Impulse is, yeah, there's some applications of it. And in particular, one of them is written right here. I didn't write this down, but let me go and write this down here. That second thing is referred to as the impulse momentum theorem. And I haven't looked ahead on this one, so I think we might see some example with that, but I'm not sure how deep we'll go into it. But basically what it says is that, okay, so impulse is defined as force times time, but the impulse momentum theorem says if you apply an impulse to an object, it will cause a change in momentum. So this second formula on the key concepts page saying I vector is equal to delta p vector, you could interpret as impulse is equal to change in momentum. But again, the kind of story behind it is we have an object, it's moving with some momentum, an impulse is applied to it, and now its momentum changes, and that impulse applied to it quantitatively is exactly equal to the change in momentum that the object experiences.